Hey Raiders, continuing our discussion of one-dimensional motion scenarios. And number 27, since you're asked a variety of things here and based on what's being asked, this is going to be one that we're ultimately going to kind of analyze a few different types of segments. So that just highlights the fact that with the more complex scenarios, like something that goes up and then changes direction and goes down, you've got to be mindful of what segment of the scenario are you analyzing. So for 27, a ball is thrown straight up in the air from the top of a 50-meter cliff and it lands in the water below after 8.3 seconds. So we've dealt with this scenario before, but it's a different combination of pieces of information that's given to us. So we'll take care of part A first. Not that you have to do A first, but what was the ball's launch speed? So since the information given to us really focuses on the entire trip, it most naturally lends itself to analyzing the whole trip, at least initially. So we'll do that. We'll analyze the whole trip. So, given information, since the ball is at the top of a 50-meter cliff for the whole trip, it's going to end up 50 meters below where it starts. So displacement, which is where something ends up compared to where it started. So displacement's negative 50 meters. And acceleration's negative 9.8 meters per second squared. And then the total time is 8.3 seconds. So we want to find part A, what was the ball's launch speed? So that's initial velocity. So this combination of variables is setting up for the quadratic. D equals VIT plus 1/2 AT squared. So negative 50 equals VI times 8.3 plus 1/2 times negative 9.8 times the time of 8.3 squared. So negative 50 equals 8.3 VI minus minus 337.561. So add 337.561 to both sides. So 8.3 VI equals 287.561. Divide both sides by 8.3. So the initial velocity ends up being approximately 34.6 meters per second. So that's part A. Part B, how fast was the ball going when it was 15 meters above the water? Well, here's a perfect example where you have to kind of customize the segment that you're dealing with, because it's not the nice, neat whole trip. It's not just up to the peak. So we're going to customize it. So we're going to analyze from the throw to 15 meters above the water. We're customizing the segment we're going to analyze for what we need. So for this one here, I'm going to make a diagram just because this is a little more complicated at this point, since it doesn't sort of fit the standard setup that we have. So this cliff is 50 meters high, and the ball's thrown upward, and we now know from doing part A that it was launched upward at about 34.6 meters per second. And we want to know when it's 15 meters above the water. So it's going to go up, reach its peak, then come back down. And so we're focusing on right here when the height is 15 meters above the water. So this visual, I think, is going to help us identify the variables that we're going to work with here. So to customize the segment that we're working with here, from the throw to 15 meters above the water. So we're going to be tracking this ball's motion from when we throw it, it reaches the peak, it's on the way down, and we're not doing the whole trip. We're going to when it's 15 meters above the water. So based off of that, our given information, initial velocity, we didn't know it before, but we figured out in part A, is about 34.6 meters per second. Acceleration is caused by gravity pulling down, so negative 9.8 meters per second squared. Now displacement. Here's where you have to distinguish between distance and displacement. Displacement is where does something end up compared to where it started. So the cliff is 50 meters high, and we're only focusing on when the ball is 15 meters above the water. So that means it has dropped from where it started another 35 meters. So displacement is negative 35 meters. So when the ball ends up 35 meters below where it started, it'll be 15 meters above the water still. So then how fast was the ball going? So we're looking for VF. It's not the ball's final velocity ever, but for this unique segment that we're analyzing, it is. So this combination of variables sets up for VF squared equals VI squared plus 2AD. So it's approximately equal to the initial velocity of 34.6 squared plus 2 times negative 9.8, the acceleration, times the displacement of negative 35, because we're focusing on a point in time when the ball's 35 meters below where it started. So 34.6 squared is about 1197.16. And then negative times a negative will be positive. So 686. So the final velocity squared equals 1,883.16. Take the square root of both sides. And we get about 43.4 meters per second. I want to talk about this a little bit here before we move on. Now, we've talked about velocity, acceleration, displacement being vector quantities where direction matters. So when the question said, how fast was the ball going? Now that use of the word fast is a little vague, so we can report our answer as speed or velocity. So we can say it's going 43.4 meters per second. That's fine. So the speed is approximately 43.4 meters per second when it's 15 meters above the water. But if we were going to say it's velocity, now we're crossing over into it has to be a vector and we have to indicate direction. So for speed, you can just refer to the quantity of 43.4 meters per second. But if we're going to describe its velocity, now we have to indicate direction. So here's where you have to separate the pure math from the physics application of it. Mathematically, when you take the square root of 1,883.16, you're going to get a positive answer. But velocity is a vector, so we have to indicate direction. Well, when it's 15 meters above the water, it's on the way down. So we would manually put the negative sign in ourselves. So I'm certainly not out to get you on that, but just pay attention to the wording of the question. If the question had said, what is the ball's velocity when it's 15 meters above the water, then you'd have to describe its velocity indicating direction, because velocity is a vector. You'd have to say negative 43.4 meters per second. But if the question just more generically says, what is the ball's speed or how fast is it going, then you can just report it as 43.4 meters per second without having to indicate the negative sign. So I'm not out to get you on that, but just make sure you're paying attention to the wording of the problem there. And then finally, part C, so that was part B. How long will it take the ball to return to the height from which you threw it? So now, again, asking something different, we can analyze this a different segment here. So how long will it take the ball to return to the height from which you threw it? So in other words, we're just looking at a time up and time down situation like you had caught the ball at the same height from which you threw it. So I'll call this segment from the throw to back to you. And you can go about this a couple different ways. So the initial velocity that we had figured out from part A earlier is approximately 34.6 meters per second. And the acceleration the entire time is going to be negative 9.8 meters per second squared due to gravity. Now you got a couple different ways you can go with this here. If we're going from the throw to when it comes back to you, You can either look at it as displacement is 0 because it ends up right back at the height from which it started, or you can also focus on the symmetry of motion. What happens on the way up happens on the way down. So if it leaves your hand going 34.6, it's going to come back to your hand on the way down going approximately negative 34.6 meters per second. You can use either of those variables there, and then ultimately we're trying to find time. So the last time this came up, I stuck with this original combination of variables, and we did the quadratic. So just to mix it up, here I'll use VF instead. So these variables along with VF, so we can do VF equals VI plus AT. So it's going to end at a velocity of negative 34.6 meters per second. That's how fast it's going to be going when it comes back to your hand. And you threw it up at positive 34.6 meters per second. So negative 34.6 equals 34.6 minus 9.8 t. Subtract 34.6 from both sides. So negative 69.2 equals negative 9.8 t. Divide both sides by negative 9.8. So notice a negative divided by negative will give us a positive time, which it should. So this ends up being a time of about 7.1 seconds to get back to your hand. Now, reflect a little bit. That's a fair amount of time to just come back to your hand. But as a kind of partial check that you did this right, notice that it's less than the total time it was in the air. And while it does take a fair amount of time, we also threw it pretty fast, so it should take a fair amount of time to come back to you. So if that total time there kind of struck you as being like, wow, that's pretty big, it's good to reflect on it. But upon reflection, that does seem to kind of make sense compared to other things in the problem. All right, Raters, if you have any questions, you know how to get a hold of me on the Remind app.